Hello, welcome to the next lecture in the NPTEL course on Haskell. So far in this course, we have been looking at various features of Haskell, how you can use Haskell to do basic programming tasks. We have looked at various things like defining functions, defining your own data types, input, output, and so on. Uh, it involved a lot of mm, specific features of Haskell. That is what we have been seeing so far. We can solve nice problems, and with whatever we have learned so far, we can already do quite a fair bit of programming. We have seen how to program with lists, which is very powerful. So, in the next half of the course, we will look at more conceptual topics. We will be looking at several fundamental algorithms, especially for sorting, and a few graph algorithms, just a few, okay. And then we will look at various data structures, okay. Data structures like stacks, queues, binary search trees, etc. So, that will be the next half of the course. But before we do all that, one of the most important things that we need to address is how do you measure your programs. Yeah, so we write programs, we write one algorithm for a problem, there is another, maybe a different idea for a problem. How do you know which is better? You need to see what the running time of the program is really, but it might not be feasible to actually do the program and then run it on the machine to find out how much actual time it takes, because there is variance across different machines. So, we need to theoretically figure out an estimate of the running time, okay. That is what we will be looking at in this lecture, and towards the end we will be looking at some example programs and what their running time is, and also we will introduce sorting in this lecture itself towards the end. Okay, let us begin. We already know that in Haskell computation is just reduction, okay. So, you have a program like reverse empty list is empty list, reverse of x followed by x's is reverse x's plus singleton x. Then if you go to GHCA and you if you write this expression, then GHCA will just proceed as follows. It will first try to do reverse of 1, 2, 3, reverse of 2, 3, 4, and this itself is reverse of and this itself is reverse of 3, 4 itself is reverse of the tail, which is 4 plus singleton list 3, and then you have to do the plus 2, then you have to do the plus 1. Reverse of 4 is reverse of empty list plus singleton 4. Plus singleton 2 plus 1. Reverse of empty list is empty list. So, now you will get empty list plus 4 plus 3 plus 2 plus the singleton list 1, which will eventually go to 4, 3, 2, 1. Right. So, this is how computation happens. This is no different than starting from 1 plus 2 times 3 plus 5 and then going to 3 times 3 plus 5, 3 times 8 and then 224. Okay, this is just like reducing an arithmetic expression, you are just rewriting an expression using user defined rules. Okay, this all this we saw already in a previous lecture. Now, so you apply, so definitions, if you want to apply a definition of reverse, let us say to a value like 1, 2, 3, 4, you are just applying rewrite rules. Okay, and one way of measuring efficiency of a program is just to count the number of reduction steps. So if you have to do reverse of 1, 2, 3, 4, you can see the program itself is given by this. Reverse of empty list is empty list, reverse of x followed by xs is reverse xs plus plus singleton x, right. So now if you want to count the, if you want to measure the amount of time taken, one way would be to say that I will count the number of reduction steps that happen. The number of reduction steps that happen when you try to evaluate reverse 1, 2, 3, 4 is that after 5 steps or 4 steps, 5 steps, let us say, you end up at reverse of empty list plus plus singleton list 4 . Actually, after 5 steps you wouldn't even have this reverse, you are just saying empty list plus plus 4. Okay, and now this does not stop, because now we have to apply the definition of plus plus and see how long it takes. Okay, plus plus, the outermost plus plus is this, and to evaluate that you need the left hand side to be of the form x followed by xs. Okay, so it will try to reduce the left hand side, the outer, now then it has to do this plus plus, so this is the outermost, but to evaluate that it needs to evaluate this plus plus, to evaluate this plus plus it needs to evaluate this plus plus, and to evaluate this plus plus it needs to evaluate this plus plus. So this goes in the order 1, 2, 3, 4, or let me use different letters A, B, C, D, let us say. This happens first, then this happens, then that happens, and then the D happens. Okay. So now how many steps are needed to do empty list plus plus 4? Recall the definition of plus plus. Empty list plus plus y is x followed by xs plus plus y is x followed by xs plus plus y's. That is the definition. So you will first do this, it will require maybe, so after 5 steps you came here, after one more step what you get is 4 plus plus 3 plus plus 2. Okay. After one more step you will get 4 followed by 3. Let's assume it's just one more step. Technically speaking, you have to say 4 is 4 followed by empty list, and empty list, yeah, so it's just one more step, 4, 3. I don't need the parenthesis. Right. So now what is 4, 3 plus plus 2? How much time does that take? You have to again refer to the definition of plus plus. So this is 4 followed by singleton 3 and this, then this becomes 4, 3, 2, 4 followed by 3 followed by list 2, and this itself will take some time, because now you have to again say 4 followed by 3, 2 plus plus 1, and this itself is 4 followed by 3 followed by 2 plus 1. Yeah, so you see that after 5 steps you have 6, 7, 8, 9, 10, 11, 12. So it takes about 12 steps to go from reverse 1, 2, 3, 4 all the way to 4, 2, 3, 1. Okay, so this is how you count the number of reduction steps. Now it looks like it might be very painful to do this for every little computation, which is why you need to develop an intuition for quickly estimating the number of reduction steps that might happen. Okay, so and I talked about estimation, so let's bring in a little mathematical notation and some minimal bit of mathematics for this. So we typically denote the running time of some algorithm for an input size n as T of n. Okay, why do I look at input size? And not the input itself? This is the most important question, and this is the most important decision when it comes to figuring out the time complexity of programs. Yeah, so okay, so let's look at the complexity of plus plus. Plus plus attaches one list before another. In the case of plus plus, it doesn't matter what the actual input is of plus plus or reverse, only input size matters. The length of the list. Because these are polymorphic algorithms, that polymorphic functions that do not even look into the list. It doesn't matter what type the elements of the lists are. Okay, so here it's fine. So we are so we would say that T of yeah, let's try to figure that out. Okay, so plus plus attaches one list before another. Empty list plus plus y's is y's, x followed by x's plus plus y's is x followed by x's plus plus y's. Okay, so 1, 2, 3 plus plus 4, 5, 6 will actually be 1 followed by 2, 3 plus plus 4, 5, 6, and this itself is 1 followed by 2 followed by 3 plus plus 4, 5, 6, which is 1 followed by 2 followed by 3 followed by empty list plus plus 4, 5, 6, which is this. Okay, so it took 1, 2, 3, 4 steps. So to compute x's plus plus y's, you use the second rule, length x's times, and the first rule once. Okay, the first rule is this, and the first rule is this one. The second rule is this one. The second rule is used however many times as there are elements in the first list. Okay, and the first rule is used once. So overall, the time taken for, let's say, Tmn is the time taken to do number of steps. X's plus plus y's, where x's is of length m and y's is of length n. If we denote it by that, then Tmn is equal to m plus 1. Okay, so and it is clear from the definition of plus plus also that the number of steps does not depend on the length of the second list. It does not depend on the second list at all. Okay, good. So let's look at another example. Here LM is an example where there is the number of steps taken depends on the actual input and not just the input length. Not just the input size. Okay. So LM is defined as follows: LM of I is the element you are searching for in a list. LM of I empty list is false. LM of I x colon xs is either I is equal to x or LM I xs is true. Okay. So this is the algorithm. So LM 3 23789 is LM 3 of 3789 is true. In this case, we just took 2 steps. LM3 of 24789 is LM3 of 4789 is LM3 of 8789, which is LM3 of 89, which is LM3 of the singleton list 9, which is LM3 of empty list, which is false. And now here we actually took 1, 2, 3, 4, 5, 6 steps. Okay. So the point is, both inputs are of same size. You have a number and you have a list. Both these lists are of the same length, but in one case you took only 2 steps, in another case you took 6 steps. So when there are variations across inputs like this, what you want is a worst case estimate. In the very worst case, I will still perform so well. That is what you want to say. Even in the worst case, the algorithm, the function does not take more than Tn steps. This is what you want Tn to mean, and therefore what you do is you take what is called the worst case complexity, which is the maximum running time over all inputs of size n. This is T of n. Okay, this is the most important decision that you take. This is a pessimistic estimate, as we call it. It's a worst case complexity. The worst case might not always be hit, but it is a safe estimate. Okay. If you want, you can actually do something called average case complexity, which is a more realistic measure. What average case complexity means is that this is the expected time, expected in the sense of probability, expected time or average time for the algorithm over inputs of size n. Okay. So one way to compute this would be to look at the time taken on every input of size n and then divide it by the number of inputs of size n. Okay, that's really average, but it is usually difficult to or impossible to compute this. So people therefore look at worst case as the standard measure when you talk about the time consumed by algorithms or functions. Okay. Now we make one more decision, we make one more abstraction. Rather than look at the precise worst case time for inputs of size n, we are only interested in this number of steps in terms of orders of magnitude. Okay. So you want to say about n steps or about n squared steps, yeah, around, let's say time taken is approximately, this is what you want to say. Or number of steps. yeah, approximately n steps, n squared steps, n cubed steps, etc. These are functions that are easy to understand and perhaps even visualize. And there are certain of these functions that keep occur very frequently in the analysis of algorithms. So, log n or 2 power n, n squared, n cubed. Okay. So, most of the algorithms we will be looking at will be somewhat like this. Okay. But what does this mean? So, technically speaking, you will say f of n is, you should really be saying f of n is in order of g of n, but by abuse of notation everyone says f of n equals order of g of n if there is a constant k and a number n such that f of n is less than or equal to k times g of n for all n greater than capital N. What this means is that for, if you ignore small input sizes, eventually f of n is below okay, that is what this means, below some constant factor of g of n. K times g of n. Okay. For instance, if I have a n squared plus b n plus c, that is a complex measure, that is a complex expression to handle, but you will say it is order n squared because I can always take k to be mod a plus mod b plus mod c, and mod a plus mod b plus mod c times n squared is always greater than or equal to a n squared plus b n plus c for all n, in fact, for all n greater than or equal to 0. Okay. So, this is the kind of for all n greater than or equal to c, let us say. Yeah. Okay. So, that is why and clearly n squared is a much simpler expression to talk about. So, you will, if your algorithm, if you have a function which actually takes time 3n squared plus 5n plus 7 in the worst case on inputs of size n, then you will just say my function grows like n squared, because if you try to plot the graphs of these functions, they look very similar. Okay. That is the point. The typical complexities that we will be looking at will be things like order n log n, order n to the k, order 2 to the n, etc. And when I say order n log n, I mean log to the base 2 of n. So, we can say now that complexity of plus plus, because if you recall, the complexity of plus plus was that the second rule was used n times and the first rule was used once. So, we said T of n is n plus 1, but n plus 1 is just order n. So, we will say that the complexity of plus plus is order n, where n is the length of the first list. Okay. Fine. Complexity of elim is order n worst case, because once again we said that if the element is not in the list at all, you would have to traverse the entire list, and we came up with a measure of n plus 1, but n plus 1 is just order n. So, let us look at reverse once again. Okay. We actually tried to do this reduction of reverse 1, 2, 3, 4 all the way to 4, 2, 3, 1 and 4, 3, 2, 1, and we said it took some 12 steps or whatever, but let us try to get an estimate in the general case. Okay. What about a list of length n? Okay. So, reverse empty list is empty list, reverse of x colon x is reverse x plus plus singleton list x. Okay. So, typically what the way to solve this would be to write what is called a recurrence for T of n. This is just like writing a recursive program, except this is not a program, you are writing a bunch of equations for the time consumed. Okay. T of 0, if the list is of length 0, means that it is the empty list, you will have to do one reduction. So, you would be given reverse of empty list, you would use the first rule for reverse to reduce it to empty list. Okay. So, this takes one time. T of n, if I have a list of length n, to reverse it, I will reverse the tail, which takes time t n minus 1, and then I will have to add the, I will have to do plus plus and put this singleton x at the rightmost, but this takes time proportional to the length of the first list. In fact, it takes exactly time equal to the length of the first list plus 1, but remember, if I started with x colon xs, if this was of length n, xs is of length n minus 1, and reverse of xs is also of length n minus 1, and if I have to do plus plus of this with this will take time, length of this list plus 1. So, that is okay, n steps. Okay. So, but before you do the n steps, you have to reverse xs itself. So, that is why it is t of n minus 1 plus n. Now, whenever you have such a recursion, recurrence, you can solve for t of n and try to get an actual a simpler expression that is not recursive in this sense. Okay. Here we have two equations that and this equation on the right also the same t occurs, and that is really a recursive equation. So, you would like to take away the recursion in this, and the simplest way to do it is just to use some kind of high school math, that is all you need. You have to unroll the recurrence, okay. You have to expand the recurrence. T of n is t of n minus 1 plus n, but that itself is t of n minus 2 plus n minus 1, and t of n minus 2 itself is t of n minus 3 plus n minus 2, and so on. When do you stop? You stop when you reach t of 0, because t of 0 is 1. At that point, if you notice the pattern here, if I do t of n minus 3, I will add n minus 2 and then n minus 1 and then n. Similarly, if you have t of 0, you would be adding all numbers from 0 plus 1 till n. So, 1 plus 2 plus 3 plus all the way up to n minus 2 plus n minus 1 plus n. Okay. So, that is what you have. So, you have 1 plus 2 plus 3 plus so on up to n, but that is nothing but 1 plus n into n minus n into n plus 1 by 2. This is all just high school math. You just expand the recurrence and then you use some formula for arithmetic progression or some such that you would have learnt in school. But now, here is the important point. If you actually expand it out, this is n squared by 2 plus n by 2 plus 1, that is something like half into n squared 2n squared plus 2n plus 2 or whatever, but this does not matter at all. You can always say that this is nothing but order n squared, okay, because this grows at the same rate as n squared. So, finally, you can summarize your all these calculations by saying that t of n is order n squared for reverse. Okay. So, now you know precisely how bad this naive reserve, how bad or how good this naive implementation of reverse is, because you have to, and the main culprit is having to repeatedly do plus plus, okay. Plus plus appends one list to another and it takes time proportional to the length of the first list, okay. How do you speed up this reverse? Okay, so we have already seen this. You want to reverse into an accumulator. This is the accumulator. What does it mean to reverse empty list into an accumulator? Just return the accumulator. What does it mean to reverse x colon xs into an accumulator? You will first put x in. So, if you imagine A is this, and if you imagine that, so this is the this is the this is the head, and you have a list xs. This is A. You have xs, and you have x here, right? So, what you do is you just, this is x. So, this whole thing is transformed into, you transfer the x's, the x from the head of this list to the head of that list, okay. And if you repeatedly do this, you start with the empty list. So, let us say you have something here, and if you repeatedly, if you start with 1, 2, 3, 4, let us say, and if you repeatedly do this, you will first put one, here, okay, this will lead you to there, that will lead you to 1 and 2 on top and 3, 4, this will lead you to which should lead you to, because all you are doing is taking one element from the head of one list and putting it into the putting it at the head of another list, and this has become the empty list now. So, and you have to read it from top to bottom. So, this is actually, originally you had 1, 2, 3, 4 in this order, now you have 4, 4, 3, 2, 1 in that order, okay. So, this is how the reverse into works, but how much time does it take? Let n be the length of the list x's. So, if you look at the recurrence here, time taken to reverse, so here is the important point. The number of steps taken does not depend on the accumulator A, okay, because as you can also see, the recursion is on the second argument, okay. So, you check whether the second argument, that xs is empty or x followed by xs, and then you make a recursive call. When you make a recursive call, the second argument keeps decreasing, okay, the length of the second argument keeps decreasing. The length of the first argument increases, but that does not matter, because you are only doing recursion on the second argument, okay. This is the important point. So, T of n, time taken to reverse list of length n into an accumulator, is actually T of n minus 1 plus 1, okay. Why is this T of n minus 1? Even though the recursive call is made for reversing x's into a different accumulator, it does not matter, because you are only doing recursion on the second argument, okay. So, time taken, time for reversing a list of length n is time for reversing a list of length n minus 1 plus 1, that is all. And if you expand this recurrence, you will have T of n is T of n minus 1 plus 1, but T of n minus 1 is T of n minus 2 plus 1, and so on till you reach T of 0. T of 0 is 1. So, you are actually adding 1 plus 1 plus 1 plus 1 n plus 1 times, which is nothing but order n, okay. So, the reverse into this strategy of doing reverse into is actually much faster, okay. Good. So, let us actually see this in action in order to appreciate the difference between these the naive reverse and the faster reverse, and also in order to appreciate the difference between order n and order n squared. Let me move to VS Code, and let us actually try to let me just say rev list A, arrow list A, rev of empty list equals empty list, rev of x followed by xs is, and then I have a rev into rev into accumulator of empty list is just returning the accumulator. Rev into accumulator, the list x colon xs is nothing but rev into x followed by accumulator, the list xs, and then I say fast rev it needn't be int, it can just be any a. Fast rev is nothing but reversing into the empty list as the accumulator. Okay, so now let's save this and let us okay, there is a terminal here which I can move into the editor area. Okay, good. I can start GHCA and I can try to run the built-in reverse rev versus fast rev. Okay, so that we see the difference in actual time. Let's take a long list 1 to 10,000. Of course, there is some time that it takes to print this whole thing. So you can actually feel that this is much faster, but maybe one should try to do length of rev of 1 dot dot. Yeah, this was much quicker. In fact, if you try for larger numbers, the difference will be even more pronounced. Yeah, this takes a long time clearly because I have to do around 1 lakh squared number of operations, whereas if I do fast rev, it is just 1 lakh operations. So I would invite you to try this out yourself. This is taking too long a time, so I'll abort this. I'm not able to abort it even. I'll just quit GHCI. Yeah, I'll try length of fast rev of 1 to 1 lakh, and you'll see that the answer comes back immediately. Okay. So in practice also you can realize this difference, and if you think about it, one takes about 1 lakh steps and the other take 1 lakh squared steps, so which is clearly a high difference.